Welcome to Online Precalculus. This is section 5-5, Trigonometric Equations. All right, so we got a few objectives here. So first, we're going to find the solutions, find all solutions of a trigonometric equation. Then we're going to solve an equation with multiple angles, solve it in quadratic form. We're going to use factoring to separate different functions in trigonometric equations. We're going to use some of our identities to solve trigonometric equations. And finally, we are going to use a calculator to solve some of these equations, which actually is not easier. All right, so previous sections, we talked a little bit about trigonometric identities. The difference here with trigonometric equations is now we have an actual equation that contains a trigonometric expression with some variable like x in sine x. We've seen that some trigonometric equations are identities, right? We've proved we've used those to prove different identities. While these equations are true for every value of the variable, for the expressions are defined. In this section, we're going to consider that trig equations are only true for some things. So with our identities, we're saying any x that you put in there is going to work. Sine squared plus cosine squared, no matter what the angle is always going to give you 1. However, for a equation, we're going to actually solve for the specific value of x that makes this thing true and gives us our solutions. Okay, so the values that satisfy an equation are solutions. An example of a trigonometric equation is sine x is equal to 1/2. Let's think about this for a second. Where is the sine equal to 1/2? Hopefully, from the unit circle, you remember that a solution to this is pi over 6, because the sine of pi over 6 is equal to 1/2. Pi is not a solution because the sine of pi is equal to 0, which is not 1/2. But if you look at the graph, right, you can see that if the horizontal line is 1/2, you can see that the graph of sine x intercepts this line more than once. In fact, on just this picture, it intercepts 5 times, but it really intercepts an infinite amount of times. So pi over 6 is not the only answer. There are infinite answers. Okay, so because of the periodic nature of the sine function, there are infinitely many values for which sine x is equal to 1/2. So how are we going to represent our solutions? Well, we know a few things. So we know that pi over 6 is an answer. We also know, because it's in the first quadrant, right? X is sine is positive in the first quadrant. We also know that 5 pi over 6 in the second quadrant is an answer to sine of x is equal to 1/2. Nothing in the third quadrant, nothing in the fourth quadrant, because the sign is negative. And then to 13 pi over 6 and 17 pi over 6. Well, hopefully you notice that that is one period, and that this is another period, right? So the distance between those two is 2 pi. The distance between those two is 2 pi. Okay, so we know that pi over 6 is our answer, and any angle with a reference angle of pi over 6 is going to have the same sign. It's just going to be positive or negative based on what quadrant it's in. So that means first, second gives me my 2 answers for sine. Then any multiple of 2 pi, because of the periodic nature of the sine function, every time we add 2 pi, we're still going to get something that satisfies this equation. So that means that we can take 2 pi and multiply it by any integer we want. That's where this n comes in, and I'm going to get an answer. Okay, so these two equations now represent all possible solutions of this of our first equation. Okay. So if I wanted to figure this out, if I wanted to find the actual answers, right, I could plug in 0 for n, and I would get pi over 6, 5 pi over 6. I could plug in 1 for n, and I would get 13 pi over 6 and 17 pi over 6. And notice on my graph, those are these 4 answers. Okay. And then I could plug in -1 to get that one. Okay. So let's take this idea and then apply it to an equation involving a single trigonometric function. So unlike trying to prove an identity, we can do anything we want to both sides of the equation. Just try not to divide out, try not to lose answers. So we're going to not divide anything by both sides of with trigonometric functions. I'm going to divide out numbers, but we're just not going to divide out trigonometric functions because it won't work with dividing by 0. We'll get to that in a second. Okay, so here's what we're going to do. To solve an equation, we're going to guess what? Isolate the variable, isolate the function on one side of the equation, and then solve for the variable. Okay? So here we go. 3 sine x minus 2 equals 5 sine x minus 1. Well, let's get everything. Whoops. Let's get everything with the sine on one side. And so we're going to subtract 5 sine x from both sides. Well, 3 sine x minus 5 sine x just gives me -2 sine x. All right, add 2 to both sides. And now we get -2 sine x is equal to 1. Okay, divide out the -2 to isolate my trigonometric function. So the sine of x is equal to -1/2. Okay, once we have this isolated, once we have the trigonometric function isolated, we are going to have to rely on our knowledge of the unit circle. Okay, so I know the sine of pi over 6 is equal to 1/2. Okay, so that means any angle with a reference angle of pi over 6 is going to have a solution of either positive or -1/2. So that means that x has to be, because I want the sign to be negative, x has to be in quadrant 3 or quadrant 4. So to find an angle in quadrant 3 with a reference angle of pi over 6, we would add pi. So that's 7 pi over 6. And look on the unit circle. What is the y coordinate at 7 pi over 6? It is -1/2. Okay. There's another place on the unit circle where the y coordinate is also a -1/2, and that is in quadrant 4, and it's at 11 pi over 6. And both of these have reference angles. And let me move this over for a second. Both of these have reference angles. Whoops. There we go. Both of these have reference angles of pi over 6. Okay, but those are only 2 answers. Okay, the question didn't say find just 2 answers in between this and this. The question said solve the equation. So I'm going to assume we want to solve this equation for every possible answer. That means we need to add the period. The period of a sine function is 2 pi. So we add 2 times some integer and pi. So plus 2n pi, where n is an integer. And now this will give me every possible answer for this equation. I think I put another, no, I didn't put it. I didn't put the second part. Okay, so now we're going to concentrate on finding solutions of trigonometric equations for a specific domain. Here, this doesn't say anything. Okay, But in these next problems, we're going to limit the domain between 0 and 2 pi. So we don't have to write this extra bit. Okay, this extra bit you only need because it says just solve the equation. There's nothing else. In some of our next problems, it's going to say solve between 0 and 2 pi. Okay, that means I don't need to put that extra plus 2 pi n. I only need to put that when the question doesn't give me a specific domain. Okay, let's look at these two problems that have multiple angles. So here we have the tangent of 3 times x is equal to 1 and sine of x over 2. This angle is a multiple of 3. This angle is a multiple of 1/2. We're going to solve each of these equations between 0 and 2 pi. Notice that in interval notation, this would look like 0 to 2 pi with a parenthesis, because I'm not including this because the answer, because the period of sines and cosines is 2 pi, the answer here at 0 is probably going to be the same as 2 pi. Don't leave out any of the answers. Okay? So the way we're going to do this one now is I'm going to do a little bit of logic here. If the inside of this thing is some number and I want it to be equal to 1, the inside of the tangent function, whatever this happens to be, has to be the thing that makes the tangent equal to 1. And from your unit circle, you should know that that is pi over 4. So at pi over 4, the tangent of pi over 4 is equal to 1. So that means 3 times x has to be equal to pi over 4. Well, also don't forget that the period of tangent is pi, not 2 pi, pi. Okay, so this would give me every possible answer, but I don't want every possible answer. I only want the specific answers in between 0 and 2 pi. So what I'm going to have to do, and first of all, this is 3x, so I'm going to divide out the 3 and get that x is equal to divide by 3 and multiply by 1/3. So we get pi over 12 plus n pi over 3. This is now every solution. To get my actual solutions, I'm going to start plugging in numbers until I get a number that's too big or too small. Well, too small. Let's try too small. If I put a negative there, I get a negative number here. So no good. All right, we want it between 0 and 2 pi. So x, if n is 0, okay, we get pi over 12. If n is 1, I would get, let's go through this whole thing. So I would get pi over 12 plus 1 times pi over 3, which is pi over 12 times plus pi over 3, which is 4 pi over 12. So that is 5 pi over 12. 5 pi over 12 is less than 2 pi. Okay, so we keep going. Now we put, this will be one of my answers. Okay, now we put a 2 there. See what we get now. Pi over 12 plus 2 pi over 3 is 3 pi over 4. Well, that is between 0 and 2 pi, so that's an answer. Okay. Now we plug in a 3. And you see what we're doing here? We're just keep adding and adding and adding numbers until we get a number that is too big. So that is, when we plug in a 3, we get 13 pi over 4. Or sorry, 13 pi over 12. All right, so this is pi, 12 over 12, 13 pi over 12. So that's 13 pi over 12. Let's plug in a 4. And when we plug in a 4, we get 17 pi over 12. Still not bigger than 2. This top number has to be 24 or bigger. We plug in a 5. 5 over 3 turns into 20 over 12. So that gives me 21 pi over 12. And, oops, 21 pi over 12. And when I plug in a 6, that would give me 25 pi over 12, which is now too big. Okay, so these are my 6 answers. There's no trick. Like back here, we could have just write plus 2 pi n, right? Because it's just asking for the general solution. That's not what this is asking for. This is asking for specific solutions. All of these numbers, when you plug them into an equation, you can check on your calculator, when you plug them into this equation, it's going to give you something that has a tangent of 1. Okay? And you could try to pick out a little pattern here, and you can see that you're just adding 4 pi over 12 each time, which makes sense because you're always adding the same thing because the period of tangent is always plus pi. Unlike sine, right, there was no way to get from this one to this one, 7 to 11, that's plus 4 pi over 6, 2 pi over 3. But the next answer wouldn't have been 2 pi over 3 later. The next answer goes all the way around to this one, plus 2 pi. Okay. Let's try another one. Okay. Let's try one where we have to multiply. Okay. So when you look at this solution back here, oops, this solution, we had a number in the front that is a horizontal compression. So we're making this function have a lot of answers, right? There's a lot of places where it's going to hit 1. As opposed to this, which is a horizontal stretch, so there's going to be less answers. So first, we're going to ask ourselves, where is x over 2 equal to 3 pi over 2? Well, okay, let's think about everywhere the function, the sine, is equal to radical 3 over 2, not 3 pi over 2, radical 3 over 2. And that is at pi over 3. And every 2 pi, or x over 2 is going to be equal to, what's the other place where the sign is positive? Well, that was first quadrant. It's also in the second quadrant. Okay. And having a unit circle, either memorized or handy for this, is helpful. We're going to multiply everything by 2. So x is going to be equal to 2 pi over 3 plus 4n pi. And x is going to be equal to 4 pi over 3 plus 4n pi. Okay, so if I plug in 0 for both of these, I get that x is equal to 2 pi over 3 and 4 pi over 3. But if I plug in 1, that's already now too big. If I plug in a negative number, now we're going negative, right? I want answers between 0 and 2 pi. So it's just these two, right? This is too much to get to the next one. Okay? I'm adding 4 pi. It's not gonna work. We're gonna get something much bigger. Okay. So if we're dividing by a number, we're just gonna get a few solutions. If the number inside here is a multiplication, we're gonna get many solutions. Okay. So some trigonometric equations are in the form of a quadratic equation, like something squared plus b times something plus c, where u is my trigonometric function, like these two. Okay. To solve this, we are going to use factoring and then the zero product property. If it doesn't factor, which it won't at some point, we're going to use either the square root property easier or the quadratic formula. And that was a lot of fun. Let's try it. Okay. So luckily, this one factors. So you could sort of do a substitution if it's easier for you to see this, where we can say that u is equal to cosine of x. And so this would transform into 2u squared plus u minus 1. And that might be a little bit easier to see how this factors. You don't have to do this if you don't want to. It's just a little bit easier for some people to factor something without trigonometric terms. Personally, you're only going to use the coefficients anyway. You know that your variable term is going to be cosine x because of this pattern, right? Cosine squared, cosine, and then a constant. So I usually just skip over the step and just go to factoring right away. So let's do that. Let's just factor this into two terms. Okay, so hopefully you remember how this works. And first two terms have to multiply to 2 cosine. So it's going to be 2 cosine and 1 cosine. 2 times 1 is 2 cosine squared. That's good. The last two terms have to be multiplied together to give you 1. So both of those were prime, so not too much difficulty here. I want my middle term to be positive. So that is a negative, that is a positive. Okay. From the zero product property, we can set each of these two terms, and then if you use this technique where you factored it with u, you just replace u with cosine to get to this point right here. We're going to use the zero product property to say either one of these two could be equal to 0. So 2 cosine x minus 1 is 0, or cosine x plus 1 is 0. So here, the cosine, add 1 to both sides, divide by 2, is 1/2. And here, the cosine is negative 1. We only want these answers. So again, we can add 2 pi, but I don't even have to do that because I know that these answers, if I just look at the unit circle, these are not transformed. There's no extra number inside with the variable. So I don't even have to worry about that. So I just need to know where on the unit circle the cosine is equal to 1/2. And it is at pi over 3 in the first quadrant, and it's also positive in the fourth quadrant. So it's also positive at the angle with the reference angle of pi over 3, which is 5 pi over 3. Again, knowledge of the unit circle and a good idea of how reference angles work is helpful for this. Where is the cosine equal to 1? Well, that is at, or sorry, where's the cosine equal to negative 1? That is at pi. Okay, so we're looking at each piece separately. We're looking at this factor and this factor separately, and I'm allowed to do that because we have a product equal to 0. If you had a product equal to a number over here, this technique would not work. It must be equal to 0. Okay. Let's try this one. Okay. I could factor this because it happens to be the difference of two perfect squares, but let's use a different technique. So let's, for sine squared x, let's add 1 to both sides. Then let's divide out the 4. I can do that. I just can't divide by trig functions. I can divide out the numbers. If this was x squared is equal to 1/4, you would just simply take the square root, which is what we're going to do here. But remember that now x is equal to plus or minus 1/2. Okay, so now, or sorry, sine x. Sine x is equal to plus or minus 1/2. So now I want to know everywhere that the sine is equal to 1/2 and negative 1/2. So that is going to be 4 answers. and it's going to be all the angles in the unit circle with a reference angle of the thing where sine is equal to 1/2, which is pi over 6. So that's pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Again, we don't put the plus 2 pi n because we're only looking for these numbers right here. And yes, the answer would be pi over 6 plus 2n pi, but it would already be too big, right? So I don't need to worry about that unless there's a a number inside there. Okay. So let's use factoring to separate some trigonometric functions in an equation. Again, make sure we're using these zero product properties. So we've seen that factoring can be used to solve trigonometric equations that are in quadratic form. Could also be used to solve trigonometric equations that contain two different kind of functions like tangent, sine, tan. In this case, we're going to move all the stuff to one side. You need to have a 0 on the other side. Then you can factor and solve these two. So let's actually do this specific problem. All right, so the first thing I'm going to do is I'm going to say, okay, I'm going to move the 3 tangent x to the left side. Then I'm going to factor it out. Oops. So the tangent of x, factor it out, and I'm left with the sine squared of x minus 3 is equal to 0. I now have a product equal to 0. That is exactly what I want because now I can use the 0 product property and separate these and say that the tangent of x is equal to 0 and that sine squared x minus 3 is equal to 0. All right, I want all the answers between 0 and 2 pi. There are two places in between 0 and 2 pi that the tangent is equal to 0, and there's two places that the tangent is undefined. So here, x is equal to 0 and pi. This one, however, the sine squared is equal to 3. Okay, take the square root of both sides, and the sine is equal to plus or minus the square root of 3. If I look on my unit circle, I don't see the square root of 3 as a y coordinate anywhere on the unit circle. I see the square root of 3 over 2, and in fact, the square root of 3 is equal to, I believe it's 1.7. You hopefully should remember that the sign only goes between -1 and +1. So because this is 1.7, it is outside the domain of my sine function and therefore will never give me an answer. It is undefined. Okay, so that doesn't mean that the question doesn't work. It just means that those are the only two answers. They only come out of this piece. This piece does not give me another answer. Okay, so just remember that the sine, output of sine must be between -1 and +1. Now we can go back to section 5.1 and some of the other sections later to use some special identities to help us solve these trigonometric equations. So trigonometric equations contain more than one function on the same side, and they can't be factored like this problem that we're about to do. Maybe you could use one of our fundamental identities to help you solve this. So hopefully you remember that cosine squared, that sine squared plus cosine squared is equal to 1, which makes cosine squared 1 minus sine squared, and I can substitute it. Plus 3 sine x is equal to 0. Well, that's not great. Well, let's distribute. So that's 2 minus 2 sine squared x plus 3 sine x. We got squareds, we got no squares, we got a constant. Looks kind of like a quadratic. Maybe you should multiply everything, this entire equation, both sides, by -1 and rearrange the terms. So this turns into a positive 2 sine squared x, a minus 3 sine x, and a minus 2. Setting that equal to 0 allows me to now factor it just like a quadratic term. I'm going to need a 2 sine and a regular sine. And now I'm going to need a 2 and a 1. I'm going to put the 2 there because that would be, whoops, no, that would be a 4. Oh, yeah. So that would be 4 and a 1. We want the minus and a plus. And those are my two factors. Okay, setting them both equal to 0 gives me that the sine of x is equal to -1/2. And we have solved that part a few times already. And it is third quadrant, fourth quadrant. So that's 7 pi over 6 and 11 pi over 6. This one, however, is not defined. Okay? So there is nowhere that the sine is equal to 2. Okay? Can't be bigger than 1. So break it down again a little bit. So we saw that there's a cosine and a sine. Not great. Nothing to factor out. So we need to change one thing to the other thing. So we change this cosine into a, or this cosine squared into a 1 minus sine squared. Okay. For this one, we are going to use a different identity. So notice that this sine has just an x. This sine has a double angle. Okay, so this is one of the double angle identities. And we need to change it so they both have the same angle. And the identity that we're going to use is that the cosine of 2x is equal to 1 minus 2 sine squared x. Okay? So I can just substitute now. So we get 1 minus 2 sine squared x plus 3 sine x minus 2 is equal to 0. Now I have all the angles the same. Now I have a quadratic again. I'm going to combine like terms. These two are like terms. They're just numbers. So that's -2 sine squared x plus 3 sine x minus 1. I'm going to multiply both sides by -1 to clear that negative. Oh, minus 3. Minus 3 plus 1. I'm now going to factor this and use the zero product property to solve it. This one factors a little bit easier. 2 sine and a regular sine. These both have to be a 1. Now I just have to plug in the fact that they're both negative. So the sine of x here is going to equal to positive 1/2. And the sine of x here is going to equal to a positive 1. Now both of those have answers. This one has two answers. The sine is equal to 1/2 in both the first and the second quadrant. So that's pi over 6 and 5 pi over 6. The sine is equal to 1 on a quadrantal angle at pi over 2. It's equal to 0 at 0 and pi, positive 1 at pi over 2, -1 at 3 pi over 2. Okay, so angles that are not quadrantal angles are usually going to give you two solutions, and the quadrantal angles are going to give you one solution. Unless it's 0, then there's two solutions. Again, knowledge of the unit circle here is really all you need to help you solve this. Sometimes before you even try to solve the problem, it's necessary to do something to both sides before using an identity. For example, in this question that we're going to do next, this equation has both a sine and a cosine. Can't factor it out. Nothing's squared, so we can't use a Pythagorean identity. But if you multiply both sides by 2, you would get a single function on the left side. And so that's what we're going to do. We're going to multiply this side by 2 and this side by 2. 2 times 1/2 is just 1. Okay, now this is an identity. It's just that the sine, well, not capital, the sine of 2x is equal to 1. So now, remember how this works from the beginning here. That means that 2x is equal to, the inside here is equal to everywhere where the sine is equal to 1. So that would be sine is equal to 1 at pi over 2 plus, now you got to do this for this one because we're going to have to solve for all my answers here. 2 pi, or 2n pi. Pi n doesn't matter. We'll do this because that's what your textbook does. Okay, 2 pi n. So again, my answers are plug in 0, comma, plug in, whoops, sorry. Before we do that, got to multiply everything by 2, or got to divide out the 2. So x is equal to pi over 4 plus n times pi. So x is going to be equal to everything that makes this between 0 and 2 pi. These are all the answers, every answer. Here's the first one, plug in 0. Here's the second one, plug in a 1. That's 4 over 4, so we have 5 pi over 4. Plug in a 2, going to be too big. That's 9 pi over 4. So these are just the only two answers. Okay. Again, and it all comes from recognizing that identity, which is a double angle identity. Okay, so let's look at another equation that contains two different functions. Sine x minus cosine x is equal to 1. Looks similar to the Pythagorean identity, but we're going to have to do something first. We're going to have to square both sides. Okay? Remember that if you raise both sides of an equation to an even power, we have the possibility of introducing extraneous solutions. Therefore, if you use this technique, not only do you have to get all the answers, but you have to check all the answers because they might not all be true. Let's check it out. So again, in order for this to get to something that I can work with, I'm going to take the sine x minus the cosine x, and I'm going to square both sides. Because what can I do here? I can't factor anything out. I could try to plug numbers in, but let's try to solve it algebraically. Okay, so factoring or squaring this binomial gives me sine squared minus 2 sine cosine plus cosine squared is equal to 1. And we're going to rearrange the terms. So we're just going to take this and this, sine squared plus cosine squared is going to be equal to 1. Equal to 1. But my next step is just subtract 1 from both sides. And we get 2 times the sine times the cosine is equal to 0. Now, just divide out the negative 2. Why would you want it there? Sine x cosine x is equal to 0. And now we have a product. So I can say that the 0 product property applies, and I could just set each one equal to 0. So x here is going to be equal to 0 and pi. X here is going to be equal to pi over 2 and 3 pi over 2. But, whoops, we have a problem because I raised both sides to an even power. So that means that I need to actually check these answers to my original equation. So my original equation says that the sine minus the cosine is equal to 1. I have to go in and actually check and see if these four equations actually work. Let's start with 0. Sine of 0 is 0. Cosine of 0 is 1. So that's 0 minus 1 is not 1. No good. Okay. Pi. Okay. The sine of pi is 0. The cosine of pi is -1. 0 minus -1 works. Okay. Pi over 2. The sine of pi over 2 is 1. The cosine of pi over 2 is 0. That works. 3 pi over 2, however, the sine of 3 pi over 2 is -1. Cosine of 3 pi over 2 is 0. No good. That's -1. So out of my four answers, I only got 2 of them to work. And the reason why that happens is because you are introducing extraneous solutions when you raise both sides to an even power. All right, let's switch over to a calculator. So in all our previous examples, the equations had solutions that were found by knowing exact values of trigonometric functions of special angles, like all the ones on the unit circle. Those are the most common. However, there's more angles on a circle than just those special angles. Okay, so for those, we're going to use our inverse trig functions on the calculator. Okay, be sure that your calculator is set to radians, which mine is not, in order for this to work. Okay, so the basics here is tangent of some numbers, tangent of some angle is 12.804. So all we have to do here is take the inverse tangent of both sides, right? And the tangent of the inverse tangent just gives me x. Okay, plugging this into my calculator gives me a number. So let's see. You got to usually press shift. 12.8044 gives me 1.49. So x is equal to 1.49, usually 4 decimal points, 4 decimals, yeah, 4929. But there's a problem, okay? Because if you remember from the end of chapter 4, the inverse tangent domain, when I plug it into a calculator, the only things it's going to give me is quadrant 1 if it's positive and quadrant 4 if it's negative. That's not what this question says. It wants every answer between 0 and 2 pi. So that means, and this is a radian, right? It's just not in the pi form. 1.4 is somewhere in the first quadrant. It's almost, you can change that to degrees if you want to know exactly. But this is in the first quadrant. I need an answer in the third quadrant, which is somewhere the tangent is also positive. So I need to add pi. So my answer is 1.4929, and also 4.6344, which is 1.49 plus 3.14, pi as a decimal. Okay, and the reason why I know I have to do that is because the way the inverse tangent works is it's only going to spit out, your calculator's only going to spit out one answer. This question wants more than that. And I could do it again, but then my answer is going to be bigger than 2 pi, which would be 6 radians. That doesn't erase. Okay. So let's try this one, which is actually a little weirder. Okay. So again, I'm just going to take the inverse cosine of both sides. Okay. And when I plug that into my calculator, I'm going to get, let's see, inverse cosine. Don't forget the negative, 0.4317. I get 2.0171. Okay, so 2.0171 is in the second quadrant because it's bigger than pi over 2. 3.14, 1.47, or 1. Yeah, 1.57. So this is how many radians it takes to get to pi over 2. So this is bigger, okay? So that means that this is in the second quadrant. Makes sense, okay? Because I want my cosine to be negative, right? I want the cosine to be negative. It's negative in the second quadrant, but it's also negative in the third quadrant. So now I need to remember how to get the actual angle, okay? And what I could do for this is I actually could calculate this. Right? If I calculated the inverse cosine of positive 4317, I should get my reference angle, okay? Because this is the negative angle, right? It's going to split out the exact angle, okay? The cosine is always going to be the same. It's just going to be different signs at each angle. And if I find the angle in the first quadrant, I will know exactly what the reference angle for this is. So we do shift cosine positive 0.4317. And I get that this is equal to, let's get rid of this so we're not less confused, hopefully. This is equal to 1.1244. Okay. This means that some angle, right, this angle in the first quadrant will be positive. Pi minus this angle will be this angle. And then pi plus this angle will be an angle in the third quadrant where the cosine is also negative. So this is my first angle, which can just be gotten from a calculator. However, you can't get the other angle without getting the reference angle. So we just add pi to this, and we get 4.266 0. Okay. And those are my two answers. Second quadrant, third quadrant. The two places where the cosine is negative. So while it seems like this should be easier, just plugging the numbers into your calculator, it can get a little bit confusing, especially when we have to solve a trigonometric equation using a quadratic formula and your calculator. Okay, so this is the fun one. All right, so let's use a substitution here so we're really not confused. So u is going to be equal to sine x, which changes this to u squared minus u minus 1 is equal to 0. That does not factor. There are no factors of 1 that subtract and give you negative 1. So we have to use the quadratic formula, which means that u is going to be equal to, and because u is equal to sine x, okay, I can just replace this where the sine x is going to be equal to these are just coefficients. Okay, the quadratic formula has no variables inside. Hopefully you remember what it is. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So that makes the sign negative negative 1. So that's 1 plus or minus the square root of 1 squared minus 4 times 1 times negative 1 all over 2. 1 plus or minus the square root, luckily these don't make it imaginary, the square root of 5 over 2. Okay, so that makes me have to calculate now a bunch of different answers. All right, first thing is the sine of x is equal to the first one, 1 plus the square root of 5 over 2, which when I plug that into a calculator, we get 1 plus the square root of 5 over 2 gives me 1.6180. So I didn't do anything yet. All I did was calculate this radical term. Okay, so now where is the sine equal to 1.6180? Well, the sine can never be equal to a number that is bigger than 1. So even if you did this on your calculator and you said, okay, let me plug this into my calculator, take the inverse sine of this term, it's going to spit you back with an error. Okay, so this whole side gives me no answers. Next, the sine is also equal to 1 minus the square root of 5 over 2, which in the calculator, as I calculate that radical term, we get negative 0.6180. Okay. So we know that we want two answers. The problem with plugging a negative number into an inverse sine is it gives you a negative answer. That's not what this question asks for. Okay, it did not ask for a number. Whoops, it did not ask for an answer. Remember, inverse sine goes like this. It's an answer in the fourth quadrant, but it's a negative angle. That's not what I want. I want a positive angle between 0 and 2 pi. Okay, so plugging this negative number into your calculator to get the inverse sine doesn't make a whole lot of sense because it doesn't give me what we want. With cosine, it was different because cosine has the inverse cosine, the domain of that is in the first and the second quadrant. So that one did work. So what I'm going to do is I'm going to take the inverse sine of the reference angle, the positive number right here. And I'm going to get uh, 0.6662. Okay, that is not my answer. Okay, that is the reference angle. That will give me my answer. I want the sign to be negative. The sign is negative in quadrant number 3 and quadrant number 4. That means x is equal to pi plus the reference angle and 2 pi minus the reference angle. And when we calculate both of these, we get that this is 3.8078 and that this one is 5.6170. Okay? And the way we're able to come up with that is because by knowing the reference angle and remembering how reference angles work, we can say that, okay, I want a number in the third quadrant. I want an angle in the third quadrant. So I'm going to start at pi, and I'm going to add this angle, this many radians to it, and I'm going to get a angle, 3.8, that has a sine of negative 0.6180. Okay, and again, you could test it, plug it into your calculator, and you should get this, right, this number when you take the sine of these two numbers. Probably the most complicated question that we've talked about in this section. All right, so what did we have to do? We couldn't factor it. We couldn't use an identity. We couldn't do anything. We recognized it was in quadratic form, but we still couldn't factor it. So we used the quadratic formula, and then we used our calculator to help us get could have been 4 answers, but this one was too big, so it only gave us 2 answers. And that was 5.5 trigonometric equations.